Okay, we are starting the next talk from Belgrade. Sana, welcome.
Hello, everybody. My name is Sana Stojanovic Durdevic, and I will talk about problems that is maybe a little bit, let's say, on a low level, like it's not very difficult theory, so everybody, I think, can comprehend the problem, and I think also the proposed solution. But I will just try to introduce you to the initial idea that we had when we started working. In general, I'm part of the automated reasoning group, and we mostly concentrate on making, like Andrea showed you, automatic theorem provers, who in most cases, Andrea made interactive theorem prover, but we like to do theorem proving by using computers in every way possible. But at one point, we got to the conclusion that we started working with machine verifiable proofs, let's say even more than working on text proofs. And we were part of people that started contributing a lot of mathematical knowledge formalized in interactive theorem provers, let's say manually, or contributing in interactive theorem proving community by automatically generating formal proofs. But at one point of the I'd say research, I wanted to take a look at the original proofs that everything starts with. Those are text proofs. So if we want to look at the, let's say, differences between textbook proofs and between machine verifiable proofs, we, as we all know, textbook proofs are meant to be readable. If they're not readable, they will not be in the textbook or not in a few editions of textbooks. So they need to be readable and easily understandable. We know that they are informal, like if we want to formalize them, then we have a lot of gaps. So, but also know, and we discovered that not only text proofs, but proofs from journals tend to have some errors, because if you write them on paper can take anything, any knowledge. So if nobody knows this is either the authors or the editors or the referees, it can contain errors, but given all that, we cannot work without textbook proofs. They are crucial for education, and basically education or introducing young students to textbook proofs is crucial for creating new mathematicians, and mathematicians are necessary for creating formal and verifiable proofs and all the other, let's say, nice stuff that we do. So we wanted to make a connection between these two as much automatically as much as possible. So our goal was to generate automatic formal proofs that we know that we expect them to be error-free, because we are using different interactive theorem provers to verify those proofs. And they showed to be crucial for science in a way that today proofs that are present in journals tend to be formally verified. So you now need to verify what you want to publish. So in order to make the connection, we started formulating a language to describe text-like proofs, but with let's say small number of sentences or types of sentences that we can use, but let's say strong enough so that we can work with high school students and university students. So we want to introduce them to interactive theorem proving and automated theorem proving, but without explicit use of interactive or automatic theorem provers. So we don't want them to see them or to learn their syntax. So let's look at one proof that we, for example, can work. I think this will be more clear if we look at the proof. theorem is one of the basic theorems from mathematical, from high schools in Serbia. And it basically says that if we have a point C that does not belong to a line, then we can construct a plane such that both of those objects lie on that plane. The proof steps are taken from the textbook. So this is not like our interpretation, that is literally like textbook proof. So we, the first thing that we know is that we need to introduce new objects in the proof, which will be the type point, and we need to introduce two different points that belong to the line P. Because those points belong to the line P, and because they are different, and because we know that the point C doesn't lie on line P, we can conclude that they are non-collinear points. Afterwards, now when we have three non-collinear points, there is one of the basic axioms, and then there exists the plane that contains all those points. And now, as we have a plane that contains two different points of line P, now we can conclude that the line P also is on that plane, and that is basically the end of our proof. But if you, let's say, listen to what I was saying and comparing that to the text on the screen, I think that you notice that I added, I added some information, like we don't have anywhere in that proof, we say that 2 points are different, but we know that that is something that needs to be explicitly stated when working with formal proofs. And there are several additions that I added, but we know that if we want to add all those additional steps, which, okay, this is not a very long proof, so there are not a lot of additional steps. So students would be able to comprehend the proof, and he would basically do that process of thinking in his own head. But if we would start to add all those technicalities, like that were needed in formal theorem proving, into textbook proofs, we will lose students. Like students first of all, they don't need it. Anybody can follow this proof, and anybody will be happy with the proof and will be, let's say, certain in that, or that's the proof of our theorem. The details that we need to add are needed for formal theorem proving. The details are even needed for informal theorem proving, but I think that every one of us, while learning geometry or learning geometry proofs, we all have that in mind. So if we draw 2 points, I think that we will all assume that those points are different without stating. And the question of whether we need to state that 2 objects are different or not is something that even Hilbert is not consistent on in his book. So he has several editions of his book where the points are stated to be different. Then in the next edition, I forgets about that, so he uses the theorem without that, let's say, condition. So those informations tend to get lost, even with people who we think of as people who really formalized geometry properly. And I say that like properly because Hilbert was taught to fix that he fixed Euclid's errors, because this type of proofs and this type of, let's say, gaps in the proof were also present in Euclid's element, because the diagrammatic reasoning that was present in elements is the same diagrammatic reasoning that we are basically using today. So we wanted to look at the basically a proof that is used for teaching geometry theorem proofs. But now we wanted to make a minimal system to describe that proof. I will not say formally, because when I say formally, I think of interactive theorem provers. So I will say semi-formally, like I still need some syntax and I still need some rules and such, but I want to make a minimal language. But what is it that I need? We need to have an axiomatic system. Okay, we need to choose in which type of axioms will use. We need to choose inference rules or the deduction system that you're working on. And of course, we need to express that statement and also the axiomatic system in the language of that system. So we actually wanted to say that even the textbook proofs, even the proofs with the diagrams is still a relevant proof. And Mark Bisem and Dmitry Hendricks said that for us, proofs explain why the theorem is true, textbook proofs, and the formal proofs basically also does the same thing, but it has a lot more details because he also needs to convince computer or the core which he's based on. So I will again return to the, let's say, two main contexts of theorem proving, where we want to keep the short proofs. We want to keep the basic idea of the proof, but we also want to be able to verify the correctness of that proof, but without explicitly showing the details that lie behind that verification. And if we look at theorem proving in general, in most cases, or in the beginning, automated theorem provers were made to just answer the question: is the given conjecture a theorem? So yes and no answer was acceptable. Okay, is acceptable even today in a lot of contexts, but interactive theorem prover gave slightly, not really slightly, but a lot of details while answering the question: is a given proof of conjecture valid? The direction in which provers are, let's say, evolving is to combine the previous two approaches, or actually to combine several automated theorem provers by their own, or to combine automated theorem provers inside to implement, not to implement, to call them from the interactive theorem prover. And some combination of those two approaches will also be used or will be presented today. But the thing that is let's say more interesting for me is that formal proofs, as I stated at the beginning, formal proofs were used to verify important mathematical knowledge, but as a lot of universities tend to teach, they actually started teaching, maybe, I'm not quite sure when it depends on the country and on the university, but they started in the last few years or last decade, or maybe even more time than that, to teach interactive theorem proving with undergraduate students, which basically gives us an opportunity to create more of formally verified mathematics or algorithms or something like that, which is exactly what we do in our course in Belgrade. We have a course on introduction of interactive theorem proving, where a part of the course is actually for students to verify different topics. We have a separate paper on that, so I will not go through that, but I think that we contributed a lot because the course is held for 6 years. We had between 30 and 60 students each year, not all of them active, but at least 50% of them were active, so it accumulates. So we have a lot of different areas that we started to work on. But again, I want to return to the informal proofs. Why? Because if somebody wants to learn interactive theorem proving, it has a very steep learning curve. So anybody who, I think everybody here knows some interactive theorem proving language, know that you really need some time to learn everything. Okay, as you progress and you learn more and more interactive theorem proving languages, it gets easier. But if you're a beginner, it really is, it can be a little bit frightening. Like, you need to enter the whole system. You need to see a lot of things that you don't need for those simple geometry textbook proofs. And we wanted to return again the idea of the informal proofs, and we want to create a system that can verify that proof. So this is our approach. We have the first 3 steps are the part that has to be done by hand. So you need to start with a statement. Of course, we assume that you have an axiomatic system and that you have axiomatic system and a statement that are expressed in your language. Then you need to write on a paper for your theorem. Then that is the part where we are starting to use a computer. We formulate that same proof in semi-formal language, and afterwards we start out. The automated part is something that was done also in a different paper, but I have to tell you a little bit about. So we used the coherent logic, which was very well suited for starting geometry theorems. Also, it is very good in generating use it as the basis for deductive systems that we can use. So coherent logic, I will give more detail, just to draw a big picture. So we can make automated theorem provers that are completely automatic, that use coherent logic. Then we can, again, completely automatically generate formal proof or verification, basically, in different interactive theorem provers. So we don't have anything, nothing is hard-coded in the system, except for the coherent logic. But statement is, of course, given to the input set of axioms or set of definitions. So everything just needs to be formulated in coherent logic. After that, we generate proof objects again in coherent logic, which now we can translate to desired languages, whatever we want to work. So let's look at coherent logic formula. This is basically a formula that is, let's say, almost the only type of formula that is used in geometry. You have some objects that are, let's say, present in the diagram or in your proof, and then you either infer some new relations over the existing objects if you don't have existential quantification, or if you have existential quantification, you then introduce new objects to your diagram if you're drawing it, or to a proof state if you're in an automated theorem. So formula is implicitly universally quantified. So existential quantification, it can be present, but it doesn't have to be present. Also, disjunctions, they don't have to be, so you can have just one, you can have empty. It really depends on the formula. For my group, let's say, Professor Mark Bezim kind of brought coherent logic to Belgrade. So that he was my first contact with coherent logic. And he has a lot of paper where he proves that coherent logic is basically strong enough to prove more or less anything. There is a general translation procedure to translate any first order logic formula into coherent logic formula, so you can fit into coherent logic formula automatically if you would like to. But I have to say that we don't use that because geometry, we are working with geometry, and geometry is already coherent logic. So we use some transformations of formula into coherent logic, but that is basically the transformations that everybody are using when working on interactive theorem proving of any geometry book. So, for example, Julien Arboux, when he was working with Tarski's book, he made the same transformations, or almost the same transformations, as I did it in my own system. Because at one point we also have a mutual paper when we, let's say, combine approaches, and we noticed that okay, we had to go like one by one. We had to check everything because my formalization is made by hand. His is also made by hand, so we had to check everything. And I think that maybe well, I cannot say 100% because of, but 99.99% we had the same transformations. So it is really a natural formulation of a natural system that is used for representing coherent or representing geometry theorems. I just have to state that in its how can I say original form, negation is not allowed, but we go around that. Well, actually, that's it. That was the best idea. So just took it. You introduce new object that actually has the meaning of the negation, but you don't use negation explicitly anywhere. So we can negate just predicate symbols. We cannot use negation over some expression or over some formula. So if you have negation over some formula, you will just transform it and like you will put it with your specific predicate symbols. Also, we use sorts for different objects, and then I say that it's more or less straightforward to formalize everything. As I said, a lot of people worked on coherent logic. So Skolem and Bezel knew they are working on coherent logic, and they said they're working on coherent logic. Narbo and Julien Narbo and Mr. Avidat, I cannot say that they didn't know, but they didn't hold it coherent logic. So, but Tarski's formalization and axiomatic system for elements. So the formulas are the same. So if somebody would look at the paper of Professor Jeremy Avidat, they would see the same type of formula like this. So it is coherent logic. It just doesn't have the title in it that says coherent logic. I think it's very, very, let's say, good logic to use for automated theorem provers. So later on, this was also done with Mark Beeson. They formulated a language for coherent logic that, or for expressing proofs in coherent logic, because we looked at the let's say, statements that were already present in other papers that everybody noticed that there are a lot of theorem provers, there are a lot of interactive theorem provers, there are a lot of, okay, we start with informal proofs, there are formal proofs in Isabel, Koch, and so on. But basically, if you know how to read a proof in one of those systems, you will more or less know how to read a proof in the other system, especially if it's a geometry proof. I'm not talking about more complicated proofs when you need to use a lot of tactics, or, you know, when you are on a, let's say, low-level set of axioms and low-level set of rules and maybe theorems, you can understand everything. So we were inspired by that, let's say, mathematical vernacular, and we wanted to make like a subset, like coherent logic vernacular. But we need to stress that cannot be a mathematical vernacular. So it cannot express everything, but we don't need it. We want it to be lightweight proof representation that can cover geometric theorems. Based on coherent logic, we created coherent logic theorem prover, and we wanted to keep with initial version actually had some start coding, but then we took it out. We used TP-TP format for input, and now we made output in those coherent logic formal that we created. So basically now our coherent logic prover can be in some way look like a black box. Now you have on the left-hand side prover, and then you have coherent logic format, proof in a coherent logic format on the right-hand side. Coherent logic format only uses these four. The proof steps are just these four. We have correspondence, case splits, assumption, and ex-false embodiment. So we don't really, it is enough to express everything that we are working on. Here we added another, let's say, additional verification of its proof structure, because we used XML-based proof format, it is proof representation. It is simple, but it allows us to add additional verification whether the proof is. We can check before exporting to interactive theorem provers. So when we put everything together, we have an input of a coherent logic formula. We have, I already told you, we have an output of coherent logic vernacular, which can be translated to formal and natural languages. But within our system, we noticed that coherent logic theorem proving is done in forward chaining mode. So it cannot be, it is not very efficient because in geometry you have several any axioms that introduces new object, any axiom that has an existential quantifier can potentially make problems with your prover, and that sometimes happens because if your proof needs to use existential quantification and you don't use any hints, and we didn't use any hints, we wanted to make the process completely automatically, and in that way we lost. We got let's say the real we could assess what was the real power of our coherent logic theorem prover, but we noticed that when we use resolution theorem provers before, we can use them again like a little black box from which we will extract just the relevant axioms that are used in the proof of that theorem. This process, I have to state, is not like 100% efficient. We will not get exactly the minimum set of axioms. We will make some kind of loop to minimize the system. But the problem is that even if we would to get rolling minimal system, this is not forward chaining, but we need an axioms for the forward chaining proof. So it can happen that this system doesn't really returns the let's say optimal set of axioms for our prover, but we can try on its own. If it doesn't successfully finishes the proof on its own, we can use resolution theorem provers. So we can, let's say, play around with that. This type of system was, maybe this will be a little bit easier to comprehend. On the one side, we have an informal proof that we need to write, semi-formal proof. On the right side, we have a set of axioms and definitions that we are working on, which can be changed. For example, when we were working with Hilbert's theorems, as we progressed, or with Tarski's book, as we progressed, we expanded set of axioms and set of definitions. So Tarski has a lot of chapters and a lot of axioms and a lot of definitions. So we will just use the axioms and definitions that were present before the current theorem. So the set of axioms is basically constantly changing. When we formulate informal proof, since we now want to verify, we verify it step by step. So basically what we do, if we have a proof for maybe 4 steps, we will try to check each of the steps individually. So we will try, for example, if we are looking at the third step, we will try to see if the third step can be proved with the assumptions of the theorem and with the first 2 steps. So we will build it like a lens, something like that. And now I would like to let's say, get back to the original proof, the original textbook proof, and to stress how we actually create semi-formal proof. We did that step by hand, so we didn't automatically generate it, but I think maybe it can be done, but we are not at that stage at the moment. We actually add steps that change the context of our proof, or when they introduce a new object, or where they conclude that some new relation between the existing object holds something like that. So For example, it can be the conclusion that certain points are collinear, or in an example that I showed you at the beginning, the conclusion that certain points are not collinear. Every time when there is a case split assumption, we need to add that to the context. So our proof will basically, it can, how can I say, if we would have textbook proofs and delete all the unnecessary non-mathematical text, we would get this proof. So it is more or less, let's say, trivial. It is trivial if you are concentrated on what you are doing. So, but I think that students, as they learn geometry, I think that they naturally get, let's say, trained to do so by their own. They just need to let's say, you need to give them a few examples to see how everything works, and I think that it can be quickly accepted. So what we initially had were just direct linear proofs, and that means that we didn't allow these steps of proofs in our semi-formal proof. So we just ignored that part, and because those were, let's say, initial experiments, and initially it looked like we can get away with it because we are using automated theorem provers, and automated theorem provers are using case distinctions on all methods, and it looked like, okay, the system will handle it, but it was really not the case, because it is more difficult for automated theorem provers to find exactly which type of case split assumption you need. So then in this talk, the main thing that we added are actually the case split assumptions. So now we can have direct linear proofs, but now we can also express proof by cases, and we can also express proof by contradiction. Also, I need to add, we can use the whole system to try to generate a proof, or to try to generate a sum or something like that, if we are not certain of the proof steps. But if we know the proof steps, we can try with larger proof steps, smaller proof steps, so we can, let's say, choose the granularity of the proof that we want to verify. And I just need to stress that because the limitations that we have are in the negation, let's say, limitation that I mentioned, because coherent logic only use negations next to the relation. So we need to, when we transform the proof, we need to look after that. So we need to transform those steps. Luckily, in geometry, it is in most cases the how can I say that they don't have any problems. Like in theory, we could have some problems, or not real problems, but we would need to assess a little bit what to do with case split assumptions is if there is a negation of junctions. So we will have to do that, but then that part could be done manually and also could be done automatically, but that is something that I think that still needs to be done. So when we formulate a step, first we use each step to define a context in which we are working on. In the beginning, our context is just the premise of the conjecture that we want to prove. So the premise, left side of the coherent logic formula. All the other steps are basically right-hand side of the coherent logic formula, but it can be potentially existentially quantified, which it doesn't have to be, but it can be existentially quantified. Conjunction of first order methods. If the current step in the informal proof is coherent logic form, or let's say right-hand side of the coherent logic formula that has disjunctions, we will not write that disjunction, but we will just write assumptions one by one in order in which they appear, And in the meantime, we need to, let's say, fill the steps. So basically, we are still either left-hand side or the right-hand side of the formula. Also, we need to stress, but this is something that is I think noticeable if you remember the geometry textbook proofs, that sometimes when you need to construct certain object, the construction of such object will not always or almost never will be at the end of the proof. You will have some objects and some assumptions, then you will introduce let's say desired object. After you introduce it, now you need to prove that it really satisfied desired conclusion. So the existent quantifier will not be at the end. So it will be somewhere, let's say, in the beginning. But the last step will be some part of, again, right-hand side of the logic formula, because you need to gather that all relevant informations that enable you to close the proof. We will use few keywords. So assume will be just for the beginning of the step, just to assume the premise of a statement that is being proved. We will use let to introduce new objects. We will use existential quantification. We will use have when we just add some new relations. When we work with when we have proof by cases, now we need to add new word, which would be suppose. And but again, we have to stress that needs to be a case split on an atomic formula. But also, what nice that we can use simple case distinctions for proof by contradiction, because we will basically write like both sides. So just the let's say obvious one will be trivial. So the first one will have to write contradiction. So naturally, we need to have a word contradiction, which will release a local assumption. Since this type of proofs now will have branching, now the process of implementing, or let's say combining everything together, is a little bit more complicated. But I don't think that would be interesting for this conference, so I didn't put that in slides, because I want to show you several small examples. First thing that I want to let's say show is that every time when in a natural language you say that you have exactly one line, exactly one plane, such, you basically need to do two things. First, you need to prove that the object exists. Then you need to prove that if two such objects exist, then they must be the same. So that is something that is always done in geometry textbooks, at least in Serbia, but I guess everybody does the same. And also, proofs often contain sentences like point D does not belong to the line AB. So what does that mean? What is AB? Like if we are being explicitly mentioning line AB, we know that this means that for different points A and B, we need to have a line that is determined by those 2 points. But such assumptions is used explicitly, I think, in Tarski's book in chapter 6. So you will go for 6 chapters without lines, and then he says, okay, Okay, now I will introduce line AB for different points A and B. So under the assumption A and B, and that assumption that those 2 points are different and that they exist, somehow even in Tarski's book, which is like you have Euclid's, we are not happy with Euclid, and there is Hilbert, we're not happy with Hilbert, and now there's Tarski. So we are happy with Tarski, but Tarski forgets about that. He has that like in a context. He knows that in the definition is under the assumption that there exists, but later on he just uses line L. So you really don't know where the line L came from. But it is somehow, well, I didn't really want to criticize everybody, but what I wanted to say is that this is present in all axiomatic systems. No matter how much somebody tries to fix it, something like this will always be present. So it is, let's say, okay to use it in textbook proofs, but if we want to write it in semi-formal proof, we need to say 2 points are different. We need to create a line L such that those points lie on that line. And then we need to construct point D such that it doesn't lie. And basically this is just one sentence. So this is not like this is part of the book, but this is not this is just to notice that we are expanding natural language proofs, but I would say by a bit. Like I think that this is acceptable because you cannot really, this is the minimal amount of information, you cannot use less. Now if we look at the first proof that I showed you, this is the same proof. We can use that semi-formal language to introduce line P. Oh, sorry. Line P is an assumption. So everything that is in the premise of the theorem is in the first line. So we have a point C, we have a line L, and we know that the point C doesn't belong to line L. And this is where we stop. Now we need to prove the rest, but now from here we go to the proof. And now each step of the proof, we have 4 steps, we have 4 semi-formal languages. So what are the changes? 2 points, we need to add that they are different, non-collinear, it's the same, we don't have to change anything. The next one is also like everything is, this is the only change that we need to add. But when we look at the textbook proof, it actually has 2 parts. The first part is that there exists a plane. A second part, that if there are, that plane is unique. So if there are 2 planes, then those 2 planes are equal. And now, what we do now? Now, we need to formulate a little bit, it looks like a little bit more complicated, but that is like we just translate it more or less one-on-one. But how do we make a uniqueness proof? Now we need to basically copy the original proof. So we need to do the same. We need to introduce 2 different points. We need to conclude that they're non-collinear. And now, since 3 points belong to first line, and since 3 points belong to the first plane and the second plane, now we can conclude this. But notice one thing: the proof steps is this is the only one that is done without any checking. This, let's say, opens up the context for us. Every following step expands the context. But before it expands the context, we try to use our automated theorem provers to verify if this can be, like we prove a lemma that's finishing here. So the next time we have this and this, and we check if we can prove that they're not linear. Next one, we have this, and this, and we try to check if we can prove this. So at the end, we have 1, 2, 3, 4, and we try to prove that they are the same. So we kind of do something between interactive and theorem proving. We just we formulate those like small lemmas and build our proof.
So, excuse me,
Yes.
so the previous slide.
Okay.
So you can say two planes, alpha and beta,
Yes.
without assuming that they are different. Because then you prove that they must be, they can't be different. But you don't assume that they are.
No. We don't assume
But
anything.
you say two, which is.
Oh, okay, but
There is only one.
okay, but that is just like we need to prove that there is one, so we assume the opposite. So we assume that there are two.
Okay. So
and when they okay, I didn't tell you that. We assume the opposite.
But you are not, that assumption is not in the.
We have planes. I just call them here alpha and beta. This R1, R2.
But there is no assumption that they are distinct.
No, we don't know anything about it. And the case split on whether they are same or they're different, it may be used if the prover will not be able to deduce this. But since this is very trivial, this step, from this step to that step, like that is one of the axioms. If you have 3 nonlinear points that belong to 2 planes, they will be the same. So we will not need case distinctions on equality of planes. But okay, yes, you're right. I should rewrite that. But I think that I literally copied it from the high school book, so it is not it is not on the same level. They will not object. They will not object to it, and
2 equals 1.
yes, yes, but yes, that is good. So I think that I literally copied it, but I will check after this lecture what exactly does it says in the book. Here we have a simple proof that uses that has proof by cases. I didn't present textbook proof because I think this is now the same as textbook proof. Okay, the only thing that I'm missing, I think, is that I'm supposed to draw a line here, and then we will be able. But it is simple. If we know that the order is A, B, C, and also A, D, C, so basically B and C are somewhere in between A and C, we need to prove that B cannot be on the left side of this. So how can we do that? We do that by making cases whether the desired conclusion is valid or the negation. And this one we can do because, as I mentioned before, coherent logic uses negation in that limited way. So for us, it is okay. We can express it. This is the first branch. This is the second branch. Okay, the second one is short one, trivial one. And the first one, actually, in a few steps, gives us contradiction. At this point, we will again have to, let's say, generate new lemmas. Like we need under this assumption, and this assumption. Now we don't verify this. This is not, let's say, on the same level as assumed, so it expands the context. Now we try to verify this. We try to verify this. We try to verify this, and then we see if we have a contradiction in the system. If we have a contradiction, now we need to basically delete all this, and when continuing with the next step, now we have a new lemma. Now we have this and this. So that is like a technical part that needs to be done in the background. But okay, let's say it is clear, and also potentially this can have more levels. It really rarely has. In geometry, you do not have too many theorems, proofs that have too many levels, but there are, I think, a few. The thing that I wanted to show you, but I don't have to. This is just like a comparison with my language. Is that I mentioned on one of the slides that in paper by Avigadin and Mama, they formalized, they defined axiomatic system that faithfully describes proof in the elements. Because as I already mentioned, Euclid's elements were criticized, but as they also say in the paper, and I completely agree with that textbook proofs, that geometry textbook proofs that use diagrams are the only kind of proofs that can be used in education. So you cannot eliminate that. You cannot say like, don't need that. We absolutely need that. And that is used not just to learn geometry, but also for students to practice like spatial reasoning, to practice logic, I think that anybody can benefit from geometry. So okay, geometry is my favorite part of mathematics, but I really think that it can really it cannot be like, let's say, forgotten. So they created axiomatic system E that faithfully represents the proofs. The proofs needs to be rewritten in similar way like I showed you that I did. So you have a natural language proofs, you have, I call that semi-formal language, they call it axiomatic system E. More or less it's the same. I actually started to create such language in parallel with them, but I didn't know about that. So when I found out about that, it was 90% the same. So it just shows that it really is, that coherent logic really is the only form of logic that can be used, or should be used for geometric proofs if you want to get readable proofs. Okay, they showed that the diagrammatic information from the diagram that can be you can read a lot of information from the diagram, but you will never see you will never have the case when you read information like congruence. You can read some information from the diagram, but that are implicit. So you will not you can, if you have some incidents or something like that, you will read it because you will draw it. Why will you draw it? Because you deduce that the point lies on a line or on the circle, something like that. They say that form of theorems is given certain objects that satisfy certain properties, you can construct certain objects that again satisfy certain properties. And this is coherent logic. It's the same. And again, objects are assumed to be distinct. That is something that I already talked about a few times. Triangles are assumed to be degenerate. And they also say that every assumption that you implicitly assume now needs to be explicitly stated in the proof. They call them construction rules, which are existentially quantified rules, and the demonstration rules without quantification. So again, they have they say that reasoning is linear. They use proof by contradiction, but also using a case distinction. So it is very similar to my system. And here we have one proof from the elements, which you have a lot of text, but what we basically do, we want to construct an equilateral triangle, and you do that by drawing a circle with the center in A, then you draw a circle with the center B, A to B, B to A, and then in the intersection point will actually be the point that will be the third point of that triangle. And what we describe first circle with the center A. Then we describe the second circle with the center B. Then we define certain C as an intersection point. This is the first. This is like construction. Now we need to prove that we constructed everything that we need. And this is the same as I told you when I was explaining about semi-formal steps. The object that is, let's say, desirable object for your theorem will be constructed early in the proof. Now we need to prove that everything is constructed well enough. And now, what can we conclude? Since B and C both lie in a circle with the center A, they are equally distant from the A. The same can be said with B. C and A are points on the circle B, and those two lengths are the same. So now we have AB equals AC and AB equals BC. So now all three of them are the same, and there we concluded the given. We arrived at the desired conclusion. This is the proof that is present in their paper. They assume that the points are different. They say they will construct the point C, such that we have an equilateral triangle. We construct first circle with the center A, second circle with the center B. We construct the intersection point, and then we have the congruences. I need to stress one. For me, it is important thing that they say in the paper that comments that are present in the brackets are just comments. They are comments from the text, but they don't consider them a part of the proof. Okay, and that is the same as I'm doing. So I will also be using just this part of the form, but I will not use the other one. So this would be my semi-formal proof, which was the same. We don't have comments. And I'm a little bit, I have a little time, but I would like to show a paper that was published last year, which is on auto-formalizing Euclidean geometry. And they did something similar. They implemented axiomatic system E in Lean. They manually formalized all the proofs in Lean. And but they use several tactics. But the things that they allow are those comments in the brackets. The one that Evigan and his part says that is not the part, that he is not using as a part of proof when he's writing proofs with the axiomatic system E. They are actually using it because this is a proof of the same proposition written in their system. What they do, they made some tactics which actually say you apply certain this can be a definition or an axiom. Like this is definition. You need to construct a triangle. Here you need to construct a triangle. Then construct intersection point. So far, everything is the same. All three systems are the same. And now, they don't mention congruence. They work with, they say, well, points B and C are on the circle with the center A. They say you can apply that axiom. And then they also do that. They say you can apply that axiom. So they lose the information congruence here. So they deviate from Amigat's axiomatic system, so that they use the comments. And also they have a strong system behind. They use SMT engines and they use some machine learning. And I'm not interested in that part, so I don't know a lot about that. I was interested about this part. They say that they use only non-construction rules when working with SMT engine. And that is, I think, a good idea because automated theorem provers with existential quantification are really not a good combination. So they keep it under control. So they can verify everything. They did verify everything. They did write everything. They just a little bit deviated from the proofs. So I would say that the language that actually I constructed is I think it can be suited for beginners, for high school students, and for that it can be like let's say similar way like Andrea's proof with natural reduction. You use small language, you use few rules, you can easily use that to let's say get student addicted to interactive theorem proving. And I like that formal proofs resemble those that are found in mathematical textbook. I really like that it is fairly similar to the axiomatic system E. So it can also, I hope, be used not just to verify existing textbooks, but also that students can use them to explore on their own how they can combine different steps, if they can prove certain lemmas or something like that. So it is not closed system, but of course there are some room for improvements. Mostly the things that is missing is that at the current point we don't remember previously proven theorems. So that is one thing that we definitely need to add. This part I left here because the trivial steps are present in the formal proofs that we generate, because we generate formal trace in interactive that can be checked in interactive theorem provers. We do not intend. We are not using them because those are trivial steps, but students might want to use them. So some trivial steps that are present there, I think that they should be hidden a little bit, because then it can increase usability for students. And of course, the last thing that well, not last, but I think that thing that can be, that can really make it usable is that if we make an online software that can practice interactive theorem proving. And also I have one slide that I will not read, but it turned out that the method that I'm using is really suitable for teaching interactive theorem proving, because it follows all the steps of the Bloom's taxonomy. But I want that to be on the slides, but I won't go through it because I don't have any more time. So thank you very much.
And suggestions. But perhaps we can take a look again on the proof with the two planes. The next one, our here. Okay, let me focus on that. I think it's fine.
Yes, the thing that I need to check, and I will check whenever there's a lecture. Plays. I need to check what is written in the text.
But I think it's fine that you want to prove that those two are the same.
Yes.
This is the there's a preposition for the natural in natural language expression. When you say two, there is some kind of presupposition that you think that they are different, but they.
Yes, but I think that this is literally like copy paste. Okay, translated from Serbian, but copy paste text from the book, because I think that not just in geometry proofs. I think that even in functional analysis or something like that, we say there exists only one, then we prove that there one actually exists, and then the other part is, let's suppose that there exists two, and we don't say if they are the same or the different. We just assume and prove that they are the same. Yes.
It's fine.
Yes. I think it is.
Also, I don't know, but it's two objects. This is a numerical quantifier, and depending on your assumptions, you may use it as at least two, or
Yes.
two.
Yes.
So
really, when we have two, it depends on the context.
Yes.
Because on the previous slide, when we or in the proof, when we are in the proof and we says it contains at least 2 points.
So it's explicit at least
it's
two.
explicit at least two. Yes. So it is at least two. They are different, two or more. So, but here we just have two. So that basically means at most. I need to check, but I think that two without anything before that, I think that it means the most, or it should.
Okay.
It should.
You assume two and you prove that they're the same. And I think it's okay.
Yes. Yes.
And it follows from the previous from the axiom.
Yes.
So
that it already exists.
I think it should be fine. So some more questions or comments? Or... Yes, welcome.
So the example that you have on the slides they are very close. So you just a few axioms and then you prove it. But some of that I remember from basic school were like there were triangles and lines, and then you have to prove that some angles are equal.
Okay, that is
much more difficult.
yes. Well, in the representation of the proof, not so much, because you just need to formulate the relations, the predicates. You just need to formulate all the predicates, and you need to add all those axioms to the axiomatic system. So I think that the problem, the things that the limitations of this approach is that I don't have addition, so I cannot prove that the two halves of the line are that I don't have some summation. So everything apart of that, I can express it with maybe more time. But I do have congruence, but I don't have summation like
Okay.
I have middle point. You know, that is not summation. Like I don't have that.
But for the student, would it be much more difficult to make all the steps, even if the system allows everything?
Can you clarify? I don't.
So this is done interactively by a student, right?
Yes.
And if we take these basic school examples, do they require more steps?
It depends on the proof. We can the system can be used just with well, not this, but this. It can work just with the theorem. It can work like a theorem prover, or like automated theorem prover. It has that was the initial option. So he can work with automated theorem provers alone, or he can formulate some lemmas or some key steps. He doesn't have to use all the steps. He can check if the proof is clear to the student. He can only add 3 steps. If the proof is more complicated, then he can make it more granular and add additional steps. So he doesn't have to use everything. But I think that this can be more read if we would to, let's say, add all the predicates somewhere on the side, like a GeoGebra or something like that. Like you can click and pull and add everything, get but with, let's say, with this meaning and with this system behind. I think it can be definitely more readable than this. But the number of steps, it is up to the student. He can make this even more detailed or less. It depends.
Since you also support automatic proving, does it mean that children can use this to cheat on assignments in job?
No, I don't. Let's say intend, or I hope that this type of systems would be used for learning. I think that's why I added the last slide, because systems like this, if students use some trivial examples, they will memorize how to translate informal language to semi-formal language. They will know which steps are needed that need to be added explicitly. They will try different steps so they can understand them. Then if they explore a lot of different steps, they will learn to apply current steps that they already learned in new situations. So I think that with trial and error, they will memorize it, learn it. They will learn how to analyze the proof, to find the errors by themselves if it is not formal, not formal, but synthetic. If they make some errors. Also, at the end, I think that they will be able to create their own solutions. I think that these types of systems with low-level axioms and low-level, I think that they are good for learning, not for cheating. It is not efficient enough so that you can cheat.
Oh, good.
So because we use coherent logic and we give automated theorem provers as essentially quantified formulas. I mentioned that the lean people, they don't do that. They use as essentially quantified formulas for machine learning algorithms because they are, let's say, smarter or know better how to handle it, but not to the SAT solvers. And I give essentially quantified formulas to automated theorem provers, and therefore the system is not strong because of that to prove everything. So they need to split.
In geometry, very quick to react to the first steps and first axioms, introducing axioms and some theorems. Very quickly, everything and the reasoning becomes very complicated with a lot of complex theorems, and especially three-dimensional, and calculating the areas. And
yes, but
so
that I have a different paper on that topic, 3D geometry. So there you need, I think that there you need to use that if we want some automation, then we need let's say proper. But not very proper, but like not coherent logic theorem provers, but resolution theorem provers or algebraic theorem provers for that, because they are more efficient and they can handle such. Because you are right. This is, I think, this can manage low level beginning. Yes, but I think in my experience that if you give students small enough examples that they are not too trivial, but that they can get interested in the area, that they really can get addicted. And if you use a computer, then there is tactile, and so they need to think, they touch something, they are happy, they have dopamine, and afterwards you can do with them whatever you like. So that is my my personal experience with students and simple systems.
but also games, geometry games, and a lot of complex reasoning, yes. Okay, thank you very much.
I think that we need
Okay, so, so now you're, please welcome. We'll stop it, we'll stop it and then we'll start. So Jörgen, welcome.
And back to the independent online document.